Okay, let's dive in. Today, we are undertaking a critical deep dive into, well, a frightening collision. The world's urgent need for more protein clashing head-on with a microscopic menace.
Yeah, we're looking at the future of global food production and a really critical risk hiding just beneath the waves: harmful algal blooms.
And our deep dive today is built around a major critical review. Could you give us the details on that source?
Sure. It's led by Andrew Ross Brown and his co-authors, and the title is Assessing Risks and Mitigating Impacts of Harmful Algal Blooms on Mariculture and Marine Fisheries.
Right, and the paper's core mission, as I understand it, is really to analyze the catastrophic impact of these harmful algal blooms, HABs, on marine farming.
Exactly that. And crucially, to recommend the scientific roadmap, we need to minimize that damage because this marine farming sector is expanding so rapidly.
The stakes really couldn't be higher for you, the global consumer, could they? I mean, managing food security for a growing planet is arguably the greatest challenge of this century.
Oh, absolutely. Aquaculture or marine farming is now the fastest growing food sector globally.
It's not just growing, it's like defining our protein future, isn't it?
It really is. Food fish production from aquaculture now officially exceeds wild capture fisheries. It's a huge milestone.
Wow.
Yeah, we're relying on this industry for over 80 million tons of protein, valued at what, $232 billion per year?
And with, what was it, 820 million people already suffering from malnutrition?
Mm-hmm. And projections putting the global population at 11.2 billion by 2100. Well, that growth is absolutely necessary. There's no question.
But, and this is the big but, that immense expansion is overshadowed by the increasing frequency of these HABs.
Yes. The review identifies them as one of the most critical threats to this entire food system.
And it seems like it's driven and intensified by climate change, pollution, and maybe even the very act of farming itself.
That's the complex picture, yeah. And if you want to understand why this matters so intensely, you really have to look at the numbers.
Okay, hit us with it.
Stop and think about this scale. The total global economic impact of HABs amounts to approximately $8 billion per year.
8 billion every year.
Every single year. That is not a one-off disaster. That's like an entire small country's annual GDP wiped out annually by microscopic algae.
That's staggering. Where does this colossal financial toll actually come from? Is it just, fish dying?
It's a combination of things, physical and economic devastation. The two major pillars of that cost are, first, the mass mortalities and finfish losing entire farm stocks, literally overnight in some cases.
Devastating for the farmers.
Totally. And second, the crushing precautionary harvesting bans imposed on shellfish.
So even if the shellfish aren't dead, you can't sell them.
Exactly. These bans preventing the sale of potentially contaminated seafood. They're estimated to cost somewhere between $3–4 billion globally each year.
Okay.
Plus, you have the unavoidable human health costs layered on top of that.
Right. And speaking of human health, this is where the review gets, frankly, terrifying. This isn't just an economic crisis. It's a public health emergency sort of hiding in plain sight on our dinner plates.
That's the absolute truth. Conservative estimates, and these are probably low, suggest around 2,000 HAB-related food poisonings occur globally each year from contaminated seafood.
2,000 cases.
And tragically, approximately 15% of those cases prove fatal.
15%? That's incredibly high.
It is. And here's the surprise nugget you really need to know about these toxins, the ones that cause the danger.
Okay.
Bivalve mollusks, so oysters, mussels, clams, they're the principal vectors. Why? Because they're filter feeders. They naturally accumulate these microalgae as they filter water.
Makes sense.
But the phycotoxins involved, the actual poisons, whether they cause paralytic shellfish poisoning, PSP, amnesic ASP, or neurotoxic NSP syndromes, fundamentally they are neurotoxins.
Affecting the nervous system.
Precisely. And here's the key detail you absolutely cannot forget. They are heat stable.
Heat stable, meaning?
Meaning you cannot cook your way out of this crisis. Boiling, frying, baking. None of it neutralizes the neurotoxin risk to human health if the shellfish is contaminated.
Wow. Okay, that fact alone changes everything about public safety and how we handle seafood, doesn't it?
Completely. It makes monitoring absolutely critical.
And the review also mentions physical damage, right? Even if no toxins are present.
Yeah, that's another angle. Beyond poisoning, HABs can harm marine life just through physical presence. Gill clogging, for example, can basically suffocate fish.
Shrimp.
Or, when these massive blooms finally die off and decay, the sheer volume of dead biomass sinking to the bottom consumes oxygen during decomposition. This leads to severe deoxygenation or hypoxia, anoxia in extreme cases.
Creating dead zones.
Exactly. And the authors highlight a deeply worrying trend linked to this decay. The number of hypoxic dead zones has apparently doubled every decade since the 1960s.
Doubled every decade. That's not just an aquaculture problem. That's an indicator of ecosystem collapse.
It's a major red flag for ocean health overall.
So, okay. We understand the immense costs, the devastating effects, both economic and ecological, and the human health risks. Let's pivot now to the complex causes outlined in the review, how these events actually get started and stick around.
Right, so first you've got the broader environmental changes.
Things like climate change.
Correct. HABs are natural phenomena. They've always occurred to some extent. But their increased frequency is unequivocally linked to human-caused anthropogenic changes. Warming sea surface temperatures, for instance.
How does warmer water help them?
Warmer surface water increases water column stratification. Basically, less mixing between the warm top layer and the colder deep water. This stability helps certain algae.
Okay.
We also see increased storm intensity, which seems counterintuitive maybe.
Yeah, you'd think storms would break them up.
They can disperse blooms, but they also wash more nutrients into coastal waters from land runoff. And critically, storms can resuspend dormant algal cysts from the seabed, seeding new blooms.
Ah, okay. So storms can be a trigger. It sounds like they need this perfect storm, almost literally, of conditions, these Goldilocks conditions the paper mentioned.
Exactly. It's a combination. They need three basic things.
Yeah.
One, the presence of the algal cells, or those dormant cysts we just mentioned. Two, highlight for photosynthesis. And three, ample nutrients, nitrogen N, phosphorus P, sometimes silicon Si, depending on the algae type.
The food source.
Right. But just as crucial are the physical conditions. Reduced turbulent mixing and increased thermal stratification, that stable water column, are key. They favor mobile species, especially dinoflagellates, which can actively swim to find the best light and nutrients.
They can position themselves in that sweet spot.
Precisely.
And there's a sort of biological secret weapon these algae possess too, right? Mixotrophy.
Yes, this is a really crucial finding the review highlights regarding the resilience of many HABs. Many harmful species are mixotrophic.
Meaning they don't just rely on sunlight, like plants.
Exactly. They're not solely autotrophic. They're versatile feeders. They can supplement their photosynthetic growth by actually ingesting smaller prey, like bacteria or other tiny algae, or by using dissolved organic nutrients directly from the water.
So even if the main nutrients, like N and P, seem low,
they can still thrive. This flexible feeding allows them to proliferate even in ocean waters that might appear nutrient-limited to purely photosynthetic organisms. They just find another food source, basically.
Which brings us, I suppose, to the central irony, or the paradox mentioned in the paper, how mariculture itself, the very industry threatened by HABs, can actually increase the risk, especially at those inshore sites.
This is where the review focuses its critical case, and it's a really important point. Waste from fed species, think finfish like salmon, or crustaceans releases dissolved nutrients directly into the surrounding water.
Like fertilizing the ocean locally?
Pretty much. And this nutrient emission from the expanding industry is predicted to increase substantially, maybe up to sixfold by 2050.
Sixfold. Wow.
These nutrients obviously promote harmful algae growth, but it's not just the quantity. They also change the chemical balance of the water.
Okay, you mentioned a term there in the notes, NP stoichiometry. Can you break that down for us a bit more conversationally?
Absolutely. Think of it like a specific recipe required for, say, a particularly toxic dinner party. The fish waste doesn't just add general food for algae, it changes the ratio of nitrogen N to phosphorus P in the water.
The balance is off.
Right. And this chemical imbalance, the specific NP stoichiometry, is exactly what certain deadly HAB species thrive on. It gives them a competitive advantage over more benign algae. It basically selects for the bad guys.
So the waste isn't just food, it's the right kind of food for the wrong kind of algae.
In many cases, yes.
Uh-huh.
And it's not just the chemical output from the farms, it's the physical infrastructure too. The net pens, the long lines for shellfish. They actually modify the local environment in ways that can encourage HABs. Well, these mariculture structures, they fundamentally change the local hydrodynamics. Think of the net pens acting like giant underwater windbreaks or baffles.
Okay, I can picture that.
They reduce current speeds and increase stratification, remember, that stable water column. Those are the exact conditions that favor those modal HAB species we talked about, the dinoflagellates.
So the farm itself creates the calm conditions the algae like.
It can, locally. The authors cite a really alarming example from China's Sanggu Bay. Massive expansion of suspended mariculture there reduced the average current speed by 40%.
40% reduction.
Yes. And it prolonged the water exchange half-life, how long it takes for the water in the bay to flush out, by 70%. The water just sits there longer, becoming more stagnant, more susceptible to bloom formation.
That's a huge physical impact. Plus, there's the risk of actually spreading the problem around, right? Where farmers unintentionally become vectors.
Yeah, that's another risk factor. The movement or relaying of potentially contaminated shellfish stocks from one area to another, or even just moving farming equipment between sites without proper cleaning.
It can carry the algae or their cysts.
Exactly. It serves as a direct vector for spreading HAB species and their associated toxins to new, previously unaffected areas.
So the question really moves from what is the environment doing to what is the farm doing to itself and the areas around it. Okay, if mariculture is contributing to the problem, what solutions does the review recommend? It seems like they focus heavily on being proactive, on ecosystem-based solutions, rather than just reacting after a bloom hits.
That's definitely the emphasis. The primary preferred approach discussed is strategic siting. That means careful spatial and temporal planning.
So choosing where and when to farm more carefully.
Precisely. Strategically siting new mariculture operations offshore, for instance, moving away from coastlines with high nutrient runoff from land and shallow, high-risk zones.
Makes sense. Get away from the triggers.
Or, if staying inshore, ensuring sites have minimum water depths and critically high natural flow rates, the paper suggests greater than 0.05 meters per second to help flush the area and prevent stagnation.
Moving offshore sounds like a good general principle, but doesn't the paper note a catch? Something about deep ocean blooms, are we just moving the problem further out?
That's the critical nuance, yeah. Moving offshore isn't a silver bullet. It helps minimize the anthropogenic contribution, the farm's own impact, and the coastal runoff influence. But some serious HABs, like certain species causing paralytic shellfish poisoning, naturally originate in open oceanic waters.
So you can site perfectly offshore and still get hit by a natural offshore bloom.
You can. So strategic siting reduces risk, especially human-enhanced risk, but it doesn't eliminate the natural background risk entirely.
Okay. The most promising holistic solution detailed seems to be integrated multi-trophic aquaculture, or IMTA. This feels like the ideal circular solution almost.
IMTA is definitely viewed as a key strategy for long-term sustainable growth and review. The concept is brilliant, really. You co-locate the waste producers, the fed species, like finfish with natural cleaners.
The extractive species.
Exactly. Things like filter-feeding bivalves, mussels, oysters, and macroalgae or seaweed.
How does that help with HABs specifically?
Well, this integrated system uses those extractive species to essentially recycle the waste nutrients, the nitrogen and phosphorus coming from the fed species. They absorb it, incorporate it into their own tissues. This directly curbs eutrophication, the over-enrichment of water that fuels blooms.
So the cleaners eat the waste from the fish cages?
In essence, yes. And the macroalgae, the seaweed, have a triple benefit, according to the review.
Oh, what are those?
1, nutrient competition. They directly compete with harmful microalgae for those dissolved nutrients. 2, shading larger seaweed canopies shade the water column below, which can suppress blooms that need high surface light. And 3, possibly allelochemical secretion. Some seaweeds release natural chemicals that actively inhibit the growth of certain harmful algae species. It's like a natural countermeasure built right into the farm design.
That sounds incredibly promising. Okay, so beyond strategic planning and integration like IMTA, technology must play a role in monitoring and prediction, right? Especially with an $8 billion annual threat. What does the review say there?
Monitoring is obviously crucial. It relies on a mix of traditional in situ analysis, literally taking water samples and counting cells under a microscope, combined with more modern real-time sensors. Things like qPCR for genetic detection of specific HAB species.
So boots on the water or buoys in the water, basically?
Yes. But we're also limited by our view of the ocean.
Mm.
Satellite remote sensing using Earth observation satellites is powerful, but it has limitations.
What can satellites actually see?
They're generally only effective for detecting high biomass surface blooms. Think of those really dense, visible red tides or green slicks. We're talking concentrations greater than about 1,000 cells per milliliter right at the surface. Species like Carenia brevis in the Gulf of Mexico, for example.
So if the bloom is, say, low density but still highly toxic, or if it occurs deeper in the water column.
Satellites are blind. Precisely. They can't detect subsurface blooms or species like Dinophysis, which can cause diuretic shellfish poisoning at relatively low cell densities and often hang out deeper down They just don't create those huge surface signatures.
Okay, that's a major gap. What about predicting blooms before they happen?
Predictive modeling is also really challenging. It's generally limited to about 1 week in advance, largely because it depends heavily on meteorological forecast accuracy, which also drops off significantly beyond a week or so.
And I recall reading that the challenge with these predictive models is that they often err on the side of caution, which sounds good for safety, but maybe bad for business.
That's the tricky balance they highlight, yes. Models that are driven predominantly by physical factors like currents and temperature forecasts often overpredict the duration of HAB events.
Meaning they predict the bloom will last longer than it actually does.
Correct. Which, from a public health perspective, is safe. The harvesting bans remain in place longer, ensuring no toxic product reaches market. But for the farmers who are waiting, sometimes desperately, for those bans to be lifted so they can sell their product.
It means immense economic losses due to unnecessary extended downtime.
Exactly. Finding that sweet spot between safety and accurate prediction is tough.
And finally, when prevention and prediction fail, or a bloom just happens unexpectedly, there are those reactive interventions, right? Trying to actively fight the bloom.
Yes, though the review stresses these are generally costly, often lack specificity, they can harm other marine life too, but sometimes they are deemed necessary.
What's the main example given?
The most established and effective reactive measure noted is the use of modified clays.
Clay. Like throwing clay in the water.
Sort of, yeah. Specially modified clays can be dispersed over a bloom. They induce flocculation, causing the HAB cells and even some dissolved toxins to clump together and sink rapidly to the seabed, effectively removing them from the water column where they pose a threat.
Does it work?
It's considered a heavy-handed method, definitely not ecosystem-based, but it has been successfully employed. In fact, it's been standard practice for emergency control of certain HABs in China since about 2014.
Interesting. Okay, so wrapping things up. Given the scale of the problem, that $8 billion annual impact we keep coming back to, what does the review identify as the biggest, perhaps most shocking gap in our current strategy?
I think the most critical takeaway, the really glaring omission highlighted, is that despite the clear severity of the threat, HAB risk assessment is still not a standard requirement when planning new mariculture sites globally.
Seriously? Even with billions in losses, we're building new farms without formally checking the HAB risk first.
Largely, yes. We have the data, we have the understanding of risk factors, proximity to runoff, local currents, historical bloom data to implement these kinds of preemptive assessments. Yet it's often not mandated in the planning and permitting process for these huge, extensive facilities.
That seems short-sighted.
It really does. The review strongly argues that further research is absolutely vital to properly quantify HAB risks associated with different farming types, fin fish versus shellfish, different structures, and especially their interaction with complex local hydrodynamics. We need better site-specific risk models.
Which leads us, I guess, to the final, really crucial question the review poses for future research, a question defined almost entirely by climate change.
Yes, the critical unanswered question for the entire industry, both inshore and the growing offshore sector, is fundamentally, how will HAB risk change in a future warmer climate?
It's not straightforward, is it? Warmer water might mean more blooms, but maybe also more storms?
Exactly. We need complex, collaborative research to untangle these interacting factors. How will increased thermal stratification, which generally favors HAB's balance against potential increases in atmospheric energy leading to more intense storms and potentially more turbulent waters, which might suppress some blooms?
And species are moving, too.
On top of all that, yes. Warming waters are already driving the poleward range extensions of many existing HAB species. They're showing up in new territories, potentially impacting aquaculture operations in regions that never had to deal with them before.
So the baseline risk map is constantly shifting.
Constantly shifting. We desperately need unified research efforts, bringing together experts on HABs, climate change modeling, and aquaculture science to tackle these future scenarios.
The challenge seems crystal clear then. We absolutely must shift from just reacting to these $8 billion annual disasters and start mandating proactive, preemptive, ecosystem-based strategies, things like IMTA, better siting, and crucially, mandatory HAB risk assessments before farms are built to secure the future of this vital protein supply.
That really sums up the urgency conveyed in the review.
Well, this has been incredibly insightful. Thank you for joining us for this deep dive into marine ecological risk and the future of global food security.